So the setup, for those of you maybe who aren't familiar with it, is how to present for 35 or 40 minutes. And then that will take a collection, and we'll talk a little bit about next week's topic. We'll also then after that have a Q&A period with the speaker, for you asking questions, get your comments for later discussion, but those will be asked questions. So to introduce this morning's speaker, it is really welcome for a very long time.
Good morning. I'm wonderful. Is Dr. Kenneth S. A very important topic that represents has been threatening us for a long, long time, and that is nuclear power. You want it? What good is it? Do we need it? This is what Dr. Schmitz, who is from the University of Missouri-Kansas City, and a number of other places as well, and he will be speaking this morning about nuclear power. Thank you.
I want to thank the organizing committee to invite me here to give my views of what nuclear energy is. Einstein said nuclear power is one hell of a way to boil water. Now, I want to point out, I do not consider myself to be an expert on anything. I am a gatherer of information which, after critical processing, I store for future use. Now, as three faces of Eve, I think nuclear energy has three personalities as reflected in these three acts. So you can think of this talk as a Whitman sampler, a flat stone shooting across the surface of information, or Reader's Digest version of nuclear energy from A to Z. In the beginning, Einstein uses metaphors, and one of the metaphors is a train. So I'm going to go back to my day when our family used trains to travel places. We would go to St. Louis Union Station. There would be 30 tracks of trains, and trains would be leaving almost every minute. Well, I'd be sitting on my train, and I look out the window, and I see the train next to me moving. And I'm thinking, gee, I wish our train would go because I really want to get on the trip. But if you're on the platform, actually, it is my train. Okay? Now, Einstein parlayed this metaphor into the theory of special relativity in 1905. There was a second paper, a three-page paper, in which the equation E equals mc squared appeared. This equation says that energy and mass are two forms of the same thing. When asked, Einstein said there was no practical application of this equation. Well, let's look at the structure of the nucleus. It's composed of protons, which have a +1 charge, and neutrons, which are neutral. Isotopes of an element have the same number of protons, but differ in the number of neutrons. So the question is, what holds all these positive charges together? So let's look at the mass of these different particles. The atomic mass unit is based on carbon-12 being defined as 12. So it's a relative mass. And if you look at the uranium-235, 92 protons and 143 neutrons, and look at their atomic masses, now what you do is you take the atomic masses of the protons and neutrons, the appropriate number, add them up, and what you get is 236.9. Well, uranium is 235.04. This difference in mass is the binding energy. Now, physicists like to equate forces with particles, and the particle in this case is the gluon, an obvious choice of names. Spontaneous decay of both isotopes of uranium. It starts out with the uranium giving off an alpha particle. And then the chain goes on with unstable particles until it eventually gets to lead, which is stable, and it stops there. And you'll notice, if you look closely, that there's a change in mass in the process of going from uranium to lead. Now, that is the energy that's in the nucleus. However, there's no way to harness this energy. It's spontaneous. So let's talk about high and low levels of radiation, the half-life, and the specific activity. Now, with respect to uranium, it decays to thorium and alpha particles, and the half-life is 703 billion years. For U-238, its half-life is 4.4 billion years. The solar system is only 4.5 billion years old, so it's a long half-life. Now, I noticed that if you multiply these two things together, you get something that's fairly constant. So I'm assuming the relationship, or drawn on this calculation, that the activity of the radioactive material is the reciprocal of its half-life. So if you take the short half-life, it's got a high level of radiation. A long half-life, it has a low level of radiation. In this regard, both forms of uranium are low-level radiation. Now, the radiation emits, the alpha particle is nothing more than a helium nucleus. The beta minus particle is an electron. The beta plus particle is a positron. Now, you'll notice the different degrees of penetration of these particles with different substances. Paper and concrete are the ones we want to focus in on. If paper can stop alpha particles, our skin can stop alpha particles. So radiation is only important if it's in what you eat, what you drink, or what you breathe. It has to get inside your body. In 1938, Hahn and Strassman bombarded uranium with slow neutrons. They discovered that barium was in their product. And so the theorists, Meitner and Fritz, did the theory, and they said, well, you split the uranium atom. And this is 33 years after Einstein's equation. They further, by analogy of division with biological cells, they named this process fission. So what is fission? You take a slow neutron and uranium-235, it's a fissile material, it can be split, and you have a certain energy in the system. That neutron is absorbed by the nucleus and it becomes unstable. So the energy goes up. So it's an unstable nucleus which splits, and it gives off fast neutrons, and the energy level is low. And so the nuclear energy we're talking about is the difference between the unstable isotope and the stable products. Born in secrecy. To harness nuclear energy, there must be a sustained nuclear reaction. Szilard in London, crossing a street, thought up chain reaction. And this is what chain reaction basically is. You have a slow neutron hit the nucleus, but it has to be a slow neutron to continue the chain reaction. So the fast neutron that's emitted has to be slowed down, and that's slowed down by a moderator. And once you get that set up, this takes off like crazy. And so you have a chain reaction. Now, the atomic bomb basics, you need a critical mass. And so you take 2 units of uranium, you rapidly put them together. And when you do that, there's a trillion fission reactions in a microsecond. That's a lot of heat in a very short period of time. And what happens when there's a lot of heat in a short period of time? Okay. Spewed forth everywhere with the explosion. Now, Szilard and Wigner were afraid that Hitler might develop the atomic bomb, so they wrote a letter to FDR about the possibility of making an atomic bomb. They gave it to Einstein to sign because he was the most famous scientist at the time, so he could get attention. So FDR signed the papers that created the Manhattan Project. The project was a secret. Congress approved funding the Manhattan Project without knowing what they were funding. The Manhattan Project was headed by Leslie Groves. He was in charge of the project. J. Robert Oppenheimer was in charge of the science. Now, the military liked secrecy. They wanted compartmentalization. They didn't want any communication between the scientists. But science advances through communication. At that time, only 2 grams of enriched uranium were present. They needed tons of nuclear material for a sustained nuclear reaction. The isotopes of uranium, the fissile material, the 235, it was less than 1% in natural uranium. So we needed 90%. So Arthur Compton was given the task of finding a company that would purify, separate the uranium from the atomic bomb. And he found one with Edward Mallinckrodt. Mallinckrodt has a pharmaceutical place in downtown St. Louis. Now, the Manhattan Project, the Belgium Putschwin has the highest concentration of natural uranium, which is only 0.1%. So there's a big problem. The U-235 that was separated, the use was for nuclear fuel. It was sent elsewhere for further refinement. The 238 was put in drums, and the reason is, well, sometime in the future we're going to recover trace elements, and this is the nuclear waste. Well, the Safe Side of the Fence documentary is done by Tony West. I'm using videos from this documentary. Tony showed this twice at Tivoli, and Rita and I went to talk to him to see the show. And Tony and I became good friends, and we still communicate after all these years. Now, Tony is not a scientist, but he does do documentary. He gets paid by being part of the broadcast team for the St. Louis Cardinals and the St. Louis Blues hockey team.
The one side of children was the next side people would one section was social or stress and then maybe choose because they want the children one the finding the children and not use conditions. And it was one side one side.
Now, the storage of nuclear waste, they put them in drums. The government had 21 acres north of St. Louis Airport. This is the St. Louis Airport site. And they stored all the drums of uranium at this site. I want to point out that Coldwater Creek is one of the boundaries of this site. And here is a picture where you can see the control tower of St. Louis Airport. Now, Mallinckrodt, when they started this project, they thought it was only going to be for a few months. So they didn't bother to put any safety equipment, because it's going to go on in a few months. Well, it lasted longer than that. It became contaminated with radioactive dust. The workers were not told of the dangers of radioactivity, because if they knew that, they would leave. So for 15 years, 1957, they were breathing this radioactive dust. Well, being contaminated, they had to find a new site. So they found a new site at Weldon Spring. And Weldon Spring was the clean one. It had all of the equipment to keep it clean, keep down the nuclear waste dust. But in the 1960s, the production was 16 tons of enriched uranium. This was 3 times that which it was built for. And as you could guess, the clean one was closed down because of contamination.
So then later on, they wanted to reopen the place, and they gave an orange during the Vietnam War. And then they thought it's still a function. Once the making wanted it to be so fun,
Eventually, the building became deteriorated, so they had to take down the building. First thing they did was build sludge ponds behind the building. And then as they took it down,
Frank, the buildings with water as we get them. So all that water and contaminant all of the experience down in the slope. We had other waters and they just, we finish very well because I don't think we're just fantastic.
Now, if you're familiar with Stateful, this is a familiar setup. But these sludge ponds, the water is highly radioactive. You didn't even need Geiger count. The area, the clean one in Weldon Quarry, was above St. Charles Wellfield and near the Missouri River. Also, about a half a mile away was Francis Howell High School. The quarry, it was originally acquired in 1940 for munitions dump. So there was a lot of hazardous material there already, but now radioactivity was being dumped there as well in drums. And over a period of time, drums corrode. And when the drums corrode, the waste material and hazardous material seep into the ground and the groundwater.
Okay, correct. And then involved in it. That's it's like you're
So this happening to basically becomes mobile. Now, on the pumping wells, 70,000 residents were dependent upon drinking water from these wells. Now, the pump basically was drawing water out of the ground. And in drawing water, the radioactive material was also being mobile and moved. St. Charles County against hazardous waste. There was an abnormal increase in the infant death. People were getting sick. So this group contacted the EPA and had a meeting in St. Charles residence. The EPA set up 75 chairs. About 2,000 people showed up. And as a result, Weldon Spring became a Superfund site. The Weldon Spring cleanup was from 1986 to 2002, and it cost $1 billion. It was monitored over a period of time, and in this case, it was over 2000 to 2011. The Department of Energy had a $1.4 billion annual budget to monitor this. And when we're looking at the uranium levels from 2000 to 2011, the target was 300 picocurie per liter, and some of this was 10 times that after all these years. So, what to do? Well, Weldon Spring disposal site was made out of concrete, so it's going to keep all the radioactivity from being gone out to the system, to the public. But it also had radioactive dirt from the quarry, because it had to clean up all the dirt so it got down to a level where radioactivity was not that important. It was 41 acres, 70 feet high, 1.5 million cubic yards of hazardous waste material. The lifetime is presumably 4,000 years. This is the lifetime of the concrete. We see bridges that need repair nowadays. Okay, let's go to an update on St. Charles. Yana Elementary School in Florissant opened in 1970. It was in the floodplain of Coldwater Creek. And just last year, October 2022, it was closed because of radioactive contamination. Cleanup of cold water is estimated to be finished by the year 2038. Let's go to the high school. Just this last month, officials called for a review of radioactive contamination effects on Francis Howell alumni. I want to talk about Chernobyl. This is out of date, but I'll give you some idea of the nuclear reactors. This is the basic components. The fuel is 235. There are control rods which absorb many neutrons. There's graphite as a moderator that reduces the speed of fast neutrons to slow neutrons for the reaction. Water has a threefold participation. It's a coolant, it's a moderator, which slows down the fast neutrons, which means it increases the reaction rate, and it also is an absorber of neutron, which means it reduces the reaction rate. There's a backup generator in case the reactor comes off the power grid. And this is a control rod at Chernobyl. It had a boron carbide that absorbs neutrons, but for some reason, they have a graphite tip which slows down the fast neutron. Another component is a high positive void coefficient. If the temperature gets real hot, the water boils, and when the water boils, it forms, so to speak, and so there's less water to absorb the neutrons. Now, on April 26, 1986, electrical engineers who had little knowledge of nuclear reactors, they wanted to know if the generator lost power, would the spinning turbine provide power to the water pumps? In other words, keep it cool. They were behind schedule, so they rapidly reduced the power level of the reactor, but that led to a buildup of neutron-absorbing products and decreased the reactivity. So what they did in response, they removed that part of the rod that decreased the reactivity to build it up again. And they had to remove all of them except 6, which means 205 were withdrawn. They continued the experiment. They turned off the power to the turbine, but that reduced the water flow. And the temperature once again started rising. And when the temperature started rising, it formed bubble. And so to counteract that, an operator hit the emergency button, which rapidly inserted the 205 control rods. Entry of the graphite tips at the beginning slowed down the fast neutrons, causing an increase in reactivity. And the reactor output jumped to about 530 megawatts in 3 seconds. That's equivalent to jumping up to 4,700 degrees Fahrenheit. The temperature of the sun is 6,000. Now, what do you have when you have a lot of energy in a small, short period of time? Slide in because Chernobyl is one of the reactors, Fukushima is another, and Three Island is another. They're all these kinds of explosions. These explosions, the percentage, the reactor grade is 3 to 5%. Weapons grade, bomb grade are 90%. This explosion was not a nuclear explosion. This explosion was a chemical explosion. The rapid change in temperature changed the liquid water to gaseous water. That's a 10,000-fold change in volume. At that high temperature, it opened up a pathway for water to generate hydrogen gas. That also exploded. So this is a chemical explosion, not a nuclear explosion. Today, there's safety issues, processes. The reactors are engaged in a dome made of concrete. Now that stops all the radiation from getting out to the outside. But what happens if there's terrorists or there's a jet plane? So what they did, they took a jet plane, put it on a track, accelerated it to 500 miles per hour, and crashed it into this concrete wall. The plane was destroyed, the concrete wall was untouched. One uranium fuel pellet creates as much energy as 1 ton of coal, 149 gallons of oil, or 17,000 cubic feet of natural gas. Why is this? Let's look at the structures. We have the size of an atom, which is 10 to the minus 10 meters. And this is the chemical energy because this is where the electrons are. Chemical energy is electron energy. The nucleus, on the other hand, is 10 to the minus 15 meters, and that's the nuclear energy. Now, we can interpret this energy in terms of a jump rope. Quantum mechanics is the wave properties of matter, and wave properties have wavelengths. So let's look at the jump rope. If you do it very simple, you get a loop where it's the lowest energy and you can jump. But if you turn it real fast, you can get a node. So this continues up the ladder. And the same thing happens in the nucleus, and you keep going up and up and up. Now, what is the relationship of the wavelengths to the energy? Well, let's look at a harp. At the short end of the harp, the pitch is high. At the long end, the long strings, the pitch is low. And in a similar way, the energy is related to the frequency of the wavelength of the description or the reciprocal of the frequency or the wavelength itself. The thing is that nuclear energy is 10,000 times the chemical energy. That's why it can substitute for so much fossil fuel. It's a blessing. The nuclear fuel pellet can be made into rods, which can be made into fuel assemblies. It's a curse. To get uranium ore, you're extracting open pit mining, extracting by underground mining, and in situ mining, the same as if you were doing fossil fuel. 1 gigawatt plant for a year, 20,000 to 400,000 metric tons of ore must be processed to obtain 28 metric tons of ore. 400,000 metric tons of ore is a little bit more than 880 billion pounds. And the consumption of 270 to 670 gallons of water per megawatt hour. The spent fossil fuels constitute the nuclear waste. About 4.5 million pounds are generated every year. 1/3 of the nuclear fuel in reactors is replaced every year to year and a half. And the spent fuel is put into a storage pool of circulating cooled water. The water prevents some of the radiation getting out. And its residence time is about 5 years. Once that time's over, it now goes into a dry storage cask made of concrete and stainless steel. And you can see the relative heights. And in terms of transporting these casks, what they did, they took a truck, put a cask on it, ran it into that concrete wall again at 80 miles an hour, and the cask came out untouched. However, the dry storage cask of spent nuclear fuel, it's on the reactor site ground. And the condition of the cask are routinely checked. That's fine. But there's 194 billion pounds of spent nuclear fuel on 77 sites in 35 states. And it's increasing at 4.5 million pounds each year. The dry cask must be maintained and funded for over 200,000 years, which is much longer than the lifetime of the nuclear power plant. And furthermore, the United States does not have a permanent storage location. So these are on the reactor grounds literally almost forever. Okay, propagated by deception. This is the third personality. This is a personal opinion based on experiences with sales pitches to bundle television, internet, and telephone. What they don't tell you is that if one goes out, they all go out. So the deception is what is not told to you. Nuclear energy is clean. Nuclear energy is said to be clean because in the production of electricity, the reactor does not produce greenhouse gases. That is wrong because they are leaving out an important component of a nuclear power plant, steam. All nuclear power plants emit 4.4 grams of carbon dioxide per kilowatt hour from released water vapor into the atmosphere. What they don't mention is the rest of the fuel cycle. The other components of the fuel cycle do produce nuclear fuel, producing nuclear fuel pellets, do produce greenhouse gases. And so you can see this is a nuclear fuel cycle. They only focus in on the reactor. They don't tell you about the rest of it. Okay? That's a deception. Now, Professor David Ruzick, he has several YouTube videos, and they're very good videos. They provide a lot of information. Now, this particular one, Dispelling the Myths of Nuclear Power, he's comparing the energy sources in terms of percentages. And we're interested in the nuclear, wind, and solar. So let's isolate those out, and let's take a look at it. Now, what I'm going to do is I'm going to give what he says And while I'm reading it to you, I want you to think about it and see if you're convinced with what he says. Now, what he starts out with is
Wind has come up by a factor of 10. That's impressive.
very impressive. Now, this is what he says. You can see the wind progression has slowed down dramatically, and the solar as well. So, if we are thinking about energy, there's one thing here that's been pretty constant: nuclear power. And it makes 20% of our electricity. And it makes no CO2. So why don't we just use more of this? Now, hopefully you form some conclusions. And let me take a drink because this is going to be a long dissertation here. Okay, so let's analyze it. Let's look at progression has slowed down dramatically and the solar as well. And you look at that and you say, okay, well, there's 10, there's 5, that's 15% decrease. There's the 16%. Oh, okay, well, that seems like it's okay. But when you plot out the data that he has shown you, what you see is the 2014 to 2019 is counted twice. It's counted in the 2006 to 2019. And anyone knows the whole is the sum of the parts, and a part of the whole is always less than the whole. Okay? But this data allows us to calculate A to B. You need two separate regions in time for comparison, and you should have the same number of years in each. Well, this is close. So I've taken his data and I've analyzed it in terms of A to B and then B to C. And what I find is going from 2006 to 2014, the increase is a factor around 6.5 to 6. And going from 2014 to 2019, the factor is 1.5 to 2.5. But if you look at the percentage increase over the two periods, it's slowed down by 22.5% and by 41.7%. I do not consider that a dramatic decrease. Let's look at the next sentence. And there's one thing here that's been pretty constant: nuclear power. Yes, you can see nuclear power is pretty constant. It's all around 8.5, 8.2. So what does that mean? Pretty constant means zero growth of nuclear energy from 2006 to 2019. Now, let's look at the next one. And it makes no CO2. Well, water to steam releases dissolved carbon dioxide into water, and other parts of the nuclear fuel cycle do generate greenhouse gases. So, why don't we just use more of this? That is a plea. He's asking you to build more nuclear reactors based on the information he gave you, which is deceptive. Nuclear waste, fuel, we're talking about referring nuclear fuel is being used once as waste. So nuclear waste is equal to spent fuel rods. Well, what is nuclear waste? Let's go back to the generation where we separate the two isotopes. Uranium hexafluoride is a volatile solid, so you can get it into the gas phase. When you get it into the gas phase, you put it into a centrifuge, and the centrifuge separates the isotopes according to their weight. And the enriched uranium and the depleted uranium is relative to the natural availability of U-235. So the enriched uranium has more, the depleted uranium has less. Now, what do we do with the enriched uranium? We're going to make fuel rods. But there's a problem, because uranium hexafluoride self-ignites above 600 degrees Fahrenheit and at high pressures. You don't want your fuel rods to ignite. So you have to convert that to a stable form of uranium, which is uranium dioxide. And you take the uranium dioxide, you make your fuel rods, you put it in a storage pool, you then put it in dry cast, and this is the nuclear waste that the proponents of nuclear energy talk about. But what about the uranium hexafluoride that depleted. You don't have to change it because you're not going to use it as fuel rods. Now, the military can use this because it's of its high density. It can be used as a tank armor-piercing bullets, but it's also put in dry storage cap. The isotope that's in dry storage cap is not counted as nuclear waste. And the Department of Energy has roughly 1.6 billion pounds of uranium hexafluoride since 2017. 7 years have passed since then. Experts who advocate nuclear power tend to focus only on the nuclear reactor. The deception, nuclear waste. Okay, you're worried about nuclear waste. What about the waste associated with solar and wind power? And this article says solar power could generate 300 metric tons of waste in the U.S. by the year 2025. After all those used panels have to go somewhere. As for wind power, 720,000 tons of blade material must be disposed of over the next 20 years. I think this person feels that this waste is put in junkyards and landfills. The wind and solar waste can be recycled. Nuclear waste cannot. Observations. In total, nuclear energy is not clean. It generates greenhouse gases, even released by nuclear power plants. Nuclear energy is not green because it generates hazardous materials, nuclear waste. Nuclear energy is not sustainable because it generates nuclear waste at a rate faster than the rate of their remediation. So, the advice is, each person in the general public should become aware of the relevant facts about nuclear energy and nuclear power to make his or her own decision. Truth, justice, and the American way. And this is the final slide. Thank you for your patience.
Wow. Yes, ma'am. It is Q&A time. But we're going to pass a basket and hope for some contributions.
Plus, let me take a moment to talk about next week's speaker. Next week, we're going to have the League of Women Voters, both from Kansas and Missouri. We're going to talk about what's on the horizon legislatively for the Kansas City metro area. So that'll be Lynn Calvert and Connie Taylor. So they'll be with us next week. So I encourage you to be here for that. And then we're going to take up a collection that is what helps us support the tech staff, make sure that we have support for our speakers, and we have practice sessions when we need those practice sessions. And then we'll be ready to start our Q&A. So, questions, if you line up over here, please speak into the mic so that everybody can hear. And remember, this is on YouTube. So we're watching the YouTube chat to see if there are any questions that emerge in there, and we will pick those up for you as well.
Thank you. That was really interesting. For people say again that one tried for nuclear power, I guess production was fairly stable over time, but the wind and solar wasn't. What is it that's changing? Is it the production level, the capacity factor, or what? Okay. This is not the one I want to actually get to.
Yes, tonight. What's the process?
Okay. Let's go down to what I did.
Wind is up by a factor of 10. That's impressive.
I'm not, well, like I said, I'm not an expert on this, but I would suspect that some of the production might, well, the technology has changed for one thing. But I think that there's been some change with respect to the association of wind and solar power, and that may be a decrease, I'm not sure. And you have to also enter in COVID a little bit on that. So to answer your question is that I don't know. I just know that it has gone down a little bit by a little bit. But it could very well be it was so popular at the beginning, there's not many more left to fulfill. I mean, I really don't know.
Well, I would suggest that I'm not I've spent quite a few years on wind power in the state of Kansas. And I'm not aware of any change in the production of wind in a particular turbine. The capacity factor, which is how much energy you get on average compared to its maximum possibility, has gone up. So I don't think there's any deterioration that I'm aware of.
Let me clarify a bit further. I'm talking about his. That
Oh, I understand it.
I would guess that you're probably more correct than he.
Oh, well, then that's.
I mean, I've seen a lot of solar panels now everywhere, and sometimes when you have a lot of land, you've got a lot of solar panels. Think on 435, there's a police station that has solar panels on its roof. So I see it going up, so I think I'm sure you're correct, but I'm going by his data and how he's, well, in my view, deceiving the public.
Uh, Thank you for touching on, solar and wind. I'm curious as to the different renewable resources, solar, wind, hydroelectric, all those kind of things. Which of those do you think is the most viable option?
I would say solar, personally, because wind is local. It's fine for Kansas, it's fine for the ocean, and solar is fine for Florida. But solar is more mobile. And as some people say, who wants those big turbines, out of the ocean? This was about 10 years ago when I said that.
Thank you.
Thank you.
But it doesn't have to be either or.
Yeah, yeah.
Sure.
It should be both and whatever else might come in the future. What should be eliminated is fossil.
Agreed.
Thank you for the presentation. It was very nice. There's one other factor that I think should be brought into consideration. I think there's one other factor that should be brought into consideration, and that is the distribution of the power. If you look at where nuclear reactors are, they're adjacent to cities by and large. Reasonably strong network connections from the source of the power to the use of the power. One of the barriers to the growth of wind and solar is we put wind fields and solar fields in the middle of nowhere.
Yes.
We do that for a strong reason, but you have to grow the grid so that you can actually migrate the use to the people who are using it. Now, the grid is not a whole thing. It's a series of regional connections, such that, for example, Texas is in part dependent on Mexico. The grid goes between Texas and Mexico. Texas is independent of California. So solar power produced in the Southwest transits over Texas and in many cases over Arizona in order to get to California. The key is to say, what is the power at its end use point, not at its generational point? It changes a whole lot of things. And the people who want you to believe in A or B ignore the cost of transmission. They will tell you, oh, this is dirt cheap, quite literally dirt cheap, at the end of the field where there's no one who needs the power. So,
Yeah, to add to that, if I may, in terms of my personal views, I didn't want to be personal in this. From my point of view, based on Tony's documentary, and from what his been advanced in nuclear power since the inception of all these other things. Nuclear power, I feel, is very safe, except what are you going to do with the waste? And to me, that is the hang up. And my point of view is, why don't the experts in nuclear power say all these other things instead of focusing in on the reactor? Because when you focus in on the reactor, oh, there is no greenhouse gas. Oh, there is no. Well, there is. But they can be honest and upfront and say what is there, what they know, just like BP knew what was going to happen with the oil spill, because what they say in truth actually enforces the possibility of increasing nuclear power. But what do you do with the waste? Yes.
What are the chances that the public is going to become knowledgeable about its information?
Almost zilch. Almost zilch. And I'm saying that based on my recent teaching areas. I gave a talk the other day on chess. How many people are going to take the time and effort to learn how to play chess because it's very complicated? How many people are going to take the time and effort to learn about nuclear power or solar power? They're going to take into consideration what is told them at face value, and they're going to weigh that out. But if the information is not true, if it's false, if it's deceptive, they're making a judgment on material information that is not correct. So I think the general public is going to have to take more time to learn the details. Like when you vote, you're supposed to learn all about the candidates before you vote. Well, when you're going to vote on nuclear power, you should know everything about nuclear power, even the bad stuff.
My guess is people spend more time knowing the NFL rankings and players of the teams. That's a time investment.
Yeah.
My question is, so you talked about the St. Louis site. That's not the only site,
Oh, no,
obviously.
no.
Do you have information about how many sites and how many super funds have been developed and how many haven't been yet?
Hanford is one site sort of like St. Louis because it did plutonium, not uranium. And there are other sites that would refine, but all the sites, the 77 sites, they all have nuclear waste on the site.
So there are
Yeah.
77.
And they're scattered throughout the United States.
And what about Superfund sites? Do you know how many of
Oh, there's
those have
quite a
been
few of them.
developed?
There's quite a few of them.
What percentage of the
I really don't know the
77?
percentages.
Okay, thank
If I can say something about Tony's DVD, you'll notice two people pictured in front. Both of them work for Mallinckrodt. The husband died of lung cancer, and their daughter, Doris, uh, fought for compensation for the workers in Mallinckrodt, and she was the only one. And now all of the Mallinckrodt workers get compensation if they can show they have developed cancer. So that's another aspect of that video. It goes into more than just nuclear energy.
I want to compliment you on a thorough assessment of this. I've known you for a while and have just a high regard for what you've just told everybody here. The other contamination that you did not mention, and I would ask you to comment on, like the uranium hexafluoride plant in Paducah. I visited there many years ago as an environmentalist and found significant groundwater contamination at that site.
Yeah.
That had no business to be there for some reason. And could you comment on why they could have migrated groundwater radiation contamination?
Why is the groundwater contamination migrates?
Yeah, the chemistry you described at the uranium hexafluoride plant didn't seem to be consistent with the discharge of that kind of contamination into the groundwater. Could you explain that?
Well, I'm not entirely sure what the question is, and I definitely don't know what the answer is.
Well,
I will say on the basis of physics, you have rain. The rain goes into the ground and goes to the bottom of the ground. Like you want to recharge the aquifers. That water is filtered through a lot of ground to get to the cavity in the ground. And any water that comes, the rain is the driving force, if you will, by building up the concentration of water on the surface. It goes underground and it can spread out through osmosis, through channels. Worms create channels, for example. If that answers your question.
No, I was asking about the chemistry of the
Oh.
uranium hexafluoride
Yeah.
process.
Yeah.
It didn't seem to have a byproduct.
Oh, I don't
there-
know the chemistry of that.
Okay, well,
Yeah.
that's what I thought.
This was a very good presentation. The kind of thing that I've spent a lot of my life trying to convince people of various things, and I'm not sure how much success I'm having. I mean, for example, the idea that the deficit is a problem is absurd. It's not true. If that's taken seriously, it'll be very destructive of the economy. But that's nobody cares about that. Nobody knows that. It's well, I have to pay my bills. I can't run a deficit. But anyway, on this, I think one thing that this I would try to translate all this into things that are, you know, you know, I like what you're doing. You're saying that all these things are they're leaving a lot of stuff out. And that's the way it always works. Somebody's getting paid to make a case, and they're not trying to do that. So the people, those of us who try to be honest about these things, have to say things in a way. And one thing I like, for example, on the infant deaths, what was the difference? What were the numbers for the infant deaths from the St. Louis thing? You mentioned the infant deaths, and putting those numbers in is good. I mean, I'm just saying that this stuff has to be slowed down a little bit and numbers emphasized and put it together that these things, you have to put all these things together to make sure to get in it right. So all these people are left out when people were trying to make a case for something. And what this really says is the thing we got to do is reduce fossil fuel use, period, including nukes. But anyway, but it's very well done.
Thank you.
I learned a lot from this.
Oh.
Do you know the answer to that question?
No, I don't.
If that's okay.
Yeah.
That's the thing you have to do. I mean, you know.
What? Yeah.
I was in Washington, D.C. when 3 Mile Island went up. I lived in Brussels when the Chernobyl cloud went over, and we couldn't buy fresh eggs, milk, meat, vegetables for a while. I then moved to London, where you couldn't buy anything that came from the hills of Wales because they were permanently irradiated by the nuclear cloud. Having said that, I think there is an inevitability about nuclear power as a combination of power sources for the future. And you're right, we need to learn to do something about that.
Thank you. Yeah, when Chernobyl went up, I was in Prague at a scientific meeting and with my advisor. And when that went up, we were convinced that we were being fed food from the Chernobyl area to get rid of the radioactive food. But that was sort of tongue-in-cheek statement. But I mean, contamination of food is an important thing with respect to reactors that blow up and spew forth radioactivity outside. But the concrete domes are going to confine that possibility. And I took out a slide where water was used as both the moderator and the coolant, and water slows down the fast neutrons. So if water is in place, it is a coolant and it also slows down the fast neutrons, to slow neutrons. But if water is drained, and that's the problem with the 3 reactors, it's the coolant water, that if water is drained in this system, the fast neutrons don't get slowed down and you don't have a meltdown because the reaction stops.
Just so we're going to be clear, we're going to have a discussion later in the library for anybody who has more comments. We have a YouTube comment or question from Craig LeBeau. Says, what about driving south on I-70? Is there any exposure in that area
No.
by driving by?
No. Yeah, from the train, you can see a nuclear reactor halfway in the middle of the state, and that's, a few miles away.
And then I guess I have a question. Have you heard about this Norway facility that they're talking about
No.
for nuclear waste, and
No.
they're designed on geological time?
Well, other countries have possibilities of nuclear waste.
Okay.
Now, well, speaking of that, there was talk a few years ago about using Yucca Mountain in Nevada. There's a problem with that. It doesn't belong to the United States. It belongs to the Indians. It's on an Indian reservation.
Do you have any action steps for citizens?
No. Yeah, read more about it and understand more about it.
Okay.
Yeah. Because in principle, like anything, and this again is my personal view, it's the people in power, the people in money that makes the decisions. And if people like Ruzick, if you're, I think Upton Sinclair said, if you're paid not to understand something, you're not going to understand it. And I think those that are in nuclear power pushing that, since there's been little growth, that's what they want to push. And they're not going to say anything else except on that. But it all depends. People power is very strong if people get together.
The 2000 that showed up on that
Yeah.
slide
Oh, yeah.
was impressive.
Yeah. But it's always been said people power is stronger than,
So we
money
need
power.
organizers.
Right. You
Yeah.
need the organizers.
Other questions? Any final comments for us?
No. Are we still being recorded?
We are.
Well, then I won't say this comment.
Okay.
What I was going to say, you said discussion afterwards. I was going to ask, do I have to show up?
Are you worried about showing
No,
up?
I'm
Oh,
not
okay.
worried.
Well, we really appreciate you being here.
Oh,
today.
thank you. I
so much.
appreciate being there. Oh, thank you. Oh, really? Good. Well, thank you. Thank you. Yes. Yeah.